Hello, yes. I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us solve some of the problems on change of basis. So it is my second video on change of basis. So in this class, let us quickly recap some of the concepts of change of basis and we solve some of the problems related to change of basis in this video. So let us look into B coordinates of x first. Suppose B is equal to set of B1, B2 and so on Bn is a basis for a vector space V and x is an element of the vector space V. The coordinates of x relative to the basis B are the weights C1, C2 and so on Cn such that x is equal to C1 B1 plus C2 B2 and so on Cn Bn. Whenever B is a basis of a vector space V, then the vectors of the vector space V can be represented uniquely as a linear combination of vectors in V. So the weights are scalars, that is the multiples of those vectors, the C1, C2 and Cn are unique. So these unique numbers are called the coordinates of x, B coordinates of x. If these coordinates are written in a column matrix form, that is called coordinate vector of x relative to B, and it is denoted by xb simply. Xb is equal to nothing but it's a column matrix of C1, C2 and so on Cn, which are the unique weights used in the linear combination of x as a product of vectors in basis B. So this xb we call it as simply as xb. Xb is the B coordinate vector of x. And C1, C2 and so on Cn are the coordinates of x. We call them as coordinates, and this matrix of column matrix of C1, C2 and so on Cn is the B coordinate vector of x. And the mapping x to xb is called the coordinate mapping, and we have seen that it is a linear transformation and 1, 1 and onto also. And let B is equal to set of B1, B2 and so on Bn, and C is equal to C1, C2 and so on Cn, B2 basis of a vector space V. Then there exists a unique n by n matrix P C from B. I will read it as P C from B such that xc is equal to P C from B xb. So this is the relation between x3 and xb. We have to multiply it with the PC from B. We call it as change of coordinate matrix. The columns of PC from B are the C coordinate vectors of the vectors in the basis P. So C coordinate vectors of the all the vectors in the basis B are taken as PC from B. That is PC from B is equal to matrix of B1C. This is our first column. B1 is the vector in the basis B and B1C is the C coordinate vector of B1. Similarly, the second column is B2C. That is C coordinate vector of B2 and so on C coordinate vector of Bn. This matrix is denoted by PC from B and it is called as change of coordinate matrix from B to C. From B to C. So that's what I am calling as PC from B. Instead of B to C, we are using this symbol, C from B. So there are some advantages which we look into this. The advantages of denoting the symbol like this instead of B to C. Multiplication by PC from B converts B coordinates into C coordinates. The columns of PC from B are linearly independent since they are coordinate vectors of linearly independent set B. Since B is a basis, it is linearly independent. So PC from B is also linearly independent. So we can find the inverse of PC from B since it is invertible. So XC is equal to PC from B XB. So here you can see that B is this side adjacent to XB and C is adjacent to XC. It is easy to remember. XC is equal to PC from B XB. If you multiply with the inverse of this one, this is a matrix and which is invertible since the columns are linearly independent. So if you multiply with the inverse of this matrix, we can get PC from B inverse XC is equal to XB. So PC from B inverse converts C coordinates into B coordinates. So this can be denoted by B from C, since it converts C coordinates to B coordinates. So it can be denoted by B from C. So this inverse PC from B inverse is equal to B from C. So this is the vector space and X is a vector in it. Then the C coordinates are denoted here. It is in Rn, and B coordinates is also another set in Rn, and the relation between these two is PC from B. So if you multiply XB with PC from B, left multiplication is XC. So further we can observe that if C1, C2 and B1, B2 are given to us, and if we need to find the PC from B, we need to construct an augment matrix C1, C2, B1, B2, and we need to convert the same into echelon form, into this form. The C1, C2 portion part is to be converted into I. Then the remaining part will be the PC from B. Similarly, if B1, B2 are taken first, then B1, B2, C1, C2 is equivalent to I, P, B from C. So if the four vectors are given, that is the vectors in two different bases are given, we can form an augment matrix with those vectors in two different bases, and we can convert the same into this form, I and some other matrix. That remaining part will be the P C from B in the first case, P B from C in the second case, as per the order of vectors we have taken. So we use these in our problems. So let us look into this first problem. Let B is equal to set of B1, B2 and C is equal to C1, C2. Be basis for a vector space V, and suppose B1 is equal to minus 2C1 plus 4C2 and B2 is equal to 3C1 minus 6c2. Find change of coordinate matrix from B to C. That is the first problem. So we need to find P, C from B as per our notation. From B to C, that is P, C from B. That is our notation. And we need to find XC also, where X is equal to 2B1 plus 3B2. So given that X is equal to 2B1 plus 3B2, so X is represented as a linear combination of vectors in B. So we can straight away write the B coordinate vector of X. That is XB is equal to 2, 3. Since the coefficients are 2 and 3 here. So XB is equal to 2, 3. It is very clear and direct from the given hypothesis. And B1C. So we need to find change of coordinate matrix from B to C, that is PC from B, in which B1C and B2C are the columns. So first we need to find B1C and B2C. So here B1C, that is C coordinate vector of B1 is equal to minus 2, 4. Since B1 is given as minus 2C1 plus 4C2. So here B is expressed as a linear combination of vectors in C. B1 is expressed as a linear combination of vectors in C. So minus 2 and 4 are the coefficients of C1 and C2. So minus 2 and 4 are the coordinates. And this is the column matrix. Minus 2 and 4 is the coordinate vector. C coordinate vector. Since here B1 is expressed as a linear combination of vectors of C. Similarly, B2C is equal to 3 and minus 6. Since B2 is equal to 3C1 minus 6C2. These two coefficients are taken here. 3 and minus 6. So B1C is minus 2, 4 and B2C is 3, 6. So change of coordinate matrix from B to C, and that is denoted by PC from B, is equal to matrix of B1C and B2C. So B1C is taken as the first column, minus 2, 4, and B2C is the second column, 3, minus 6, which we have obtained here. So now XC is equal to PC from B, XB. So this is the relation between XC and XB. So here you can observe that this B is adjacent to XB and this C is adjacent to this XC. So now PC from B is minus 2, 3, 4, minus 6, this matrix, and XB is 2, 3 as per the given hypothesis. XB is fine here, of course. XB is 2, 3. So we use this 2, 3 there. So after multiplying these two, minus 2 into 2, minus 4, plus 3 into 3, 9, plus 9. So minus 4 plus 9 is 5. And 4 into 2, 8, minus 6 times 3, minus 18. So that is minus 10. So 5 minus 10 is XC. That means X can be represented as 5C1 minus 10C2. So here we are asked to find XC, and XC is 5 and minus 10. This is the C coordinate vector of given X. In this problem, XB, X is expressed in terms of vectors in basis B. Now we are converting that into vectors of basis in C. So these are the This is XC and this is the change of coordinate matrix from B to C. Similarly, let us solve one more problem. Let B1 is equal to minus 9, 1, B2 is equal to minus 5, minus 1, C1 is equal to 1, minus 4, and C2 is equal to 3, minus 5. So here 4 vectors are given to us, and consider the basis for R2 given by B is equal to B1, B2 and C is equal to C1, C2. Find the change of coordinate matrix from B to C. So here two bases are given to us, and we are asked to find change of coordinate matrix from B to C. From B to C means we need to find PC from B. That is our notation. PC from B. We need to find that. So the matrix PC from B involves C coordinate vectors of B1, B2. So PC from B is nothing but matrix of B1C and B2C. C coordinates of B1 and C coordinates of B2 are to be found first. So B1C is not given here. So B1 is not expressed in terms of C. So let B1C is x1, x2 and B2C is equal to y1, y2. So we need to find these two. Then by definition, C1, C2 times x1, x2 is equal to B1. So now this B1 can be expressed as x1 times C1 plus x2 times C2. So x1 C1 plus x2 C2 is equal to B1. That relation can be written in matrix form as matrix of C1 C2 times matrix of x1 x2 is equal to B1. Similarly, this is the second relation. Matrix of C1 C2 into matrix of y1 y2 is equal to B2. Since the coordinates are y1 and y2 here. So these two are the matrix relations of this expression. And to solve this equation simultaneously, let us construct an augmented matrix C1 C2 B1 B2 that is equal to the vectors in C1 are written here and C2 B1 B2 are taken here, and now this is being reduced to a matrix which is equivalent to I and P C from B. So the first part should be reduced to identity matrix I. So after performing elementary row operations, we can convert this equation, this matrix into this form. So simultaneously, while using elementary row operations, the remaining entries will also change, and this will be the final shape. So 6, 4, minus 5, minus 3. So this is our B1C, 6 and minus 5, and this is our B2C, 4, minus 3. So the desired change of coordinate matrix is therefore PC from B is equal to matrix of B1C and B2C. So these two columns, these two vectors are taken as columns of this matrix, and the desired matrix is 6, 4, minus 5, minus 3. So here we have used this augment matrix C1, C2 and B1, B2, and then we converted it into a matrix with I, P, C from B. When the first part becomes I, the second part becomes P, C from B. So this is our required change of coordinate matrix from B to C. So let us solve one more similar problem. Here we are asked to find change of coordinate matrix from C to B and change of coordinate matrix from B to C. Both are asked here. In this problem also B1, B2, C1, C2 are given to us. B1 is 1 minus 3, B2 is minus 2, 4, and C1 is minus 7, 9, C2 is minus 5, 7. And consider the basis for R2 given by B is equal to B1, B2, C is equal to C1, C2. So we need to find two change of coordinate matrices from C to B and B to C also. So change of coordinate matrix from C to B, the first one is denoted by P B from C. So this is the symbol for that. This from C to B. So we can write it as P B from C. Instead of writing C to B, we are writing B from C. So for B from C, we need to first write B's. That is the vectors in the basis B. So first we are taking B1, B2 and C1, C2 in the rest of the two columns. So this is the advantage of this notation. In this notation, first B comes, so we are taking elements of B first. C later, so we are taking vectors in C in the later part. So even we are multiplying xb is equal to pb from C xc. So those formulas will automatically come from this one. It is easy to remember, of course. So this is the augment matrix we formed using B1, B2 and C1, C2. Now we need to convert them into an identity matrix. This part should be converted into identity matrix, so that first of all I am making this 0. So to make this 0, multiply the first row with 3 and add it to second row. That will give you these numbers. So minus 3 plus 3 is 0. 4 minus 6 is minus 2. 9 minus 21 is minus 12, and 7 minus 15 is minus 8. So now I need to make it 1. So using this 2, I am making this 0. Just I can subtract the first row from second row, so that I can get this one. 1053, 0 minus 2 minus 12, 8. Now I can make this as 1 by dividing it with it by minus 2. So this is the required format. Now this is I, and this is P B from C. Since we have taken B's first. So here I have taken B1, B2. So this is P B from C. We know that the matrix of C1, C2, B1, B2 is equivalent to I, P, C from B, but this is not taken now. We have taken this one, B1, B2, C1, C2. This is the order of our augment matrix. So it is equivalent to I, P, B from C. So this part is P, B from C. P, B from C is 5364. So now we have to find P, C from B also. So we can we can find that in two ways. First, we can find the inverse also. PC from B is nothing but inverse of PB from C. So since it is a 2 by 2 matrix, it is easy to find the inverse. Here I am taking the det A, 1 by det A. Here det A is nothing but 5 into 420 minus 18. That is det A. And this is adjoint A transpose. So D minus B minus C A for a 2 by 2 matrix. So simply we can get this is 1 by 2. After multiplying this 1 by 2, we will get 2 minus 3 by 2 minus 3 5 by 2. So this is our P C from P. So once we find one change of matrix in one direction, we can find the second change of matrix in the other direction by finding the inverse of the same. In 2 by 2, it is simple. Or we can do it in another way also. For higher order matrices, of course. The same method of finding P, B from C can be adopted here, but here we need to take C's, the vectors of C's, that is C1, C2 first. And vectors of the other basis B are to be taken in the next part, remaining part. So I am taking C1, C2, B1, B2 in this order. So again, all the 4 vectors are given to us in the hypothesis. So I have taken all the 4 vectors, and now I am converting it into I and some matrix, and that portion will be P C from B. And this can be made 0 by elementary operations by multiplying this minus 7 into 9 minus this one into this, and the same operations are carried to here. So that I can get this matrix minus 7 minus 5 1 minus 2. First row is same. Here 9 into 7, 9 into minus 7 plus minus 7 into 9. Here we are multiplying these two. 7 into minus 7 minus 49 plus 45, that is minus 4. Similarly here 12 and minus 10. Now I can take 2. I can divide the second row with 2 minus 2 especially, so that I can get this one. So using this 2 I can make this 0 like this. I am multiplying this with 2 and subtracting with this one into 2. So you get this one, and you can take R1 as R1 by 14, and R2 goes to R2 by 2, which will give you this matrix. Now it is I, and this is our required matrix P C from. So this is the matrix. Here you can observe that both are same. So we can find the inverse of P B from C, or we can take this method also. So there are 2 ways to find a change of matrix, second change of matrix. First one is calculated. So this is change of matrix from B to C. And there are more similar problems. In the following exercises, let B is equal to B1, B2 and C is equal to C1, C2 be basis for R2. In each exercise, find the change of coordinate matrix from B to C and the change of coordinate matrix from C to B. So 4 vectors, 4 different problems are given. In each problem, 4 vectors are given. So let us do these problems in Excel lab. Let us go to Excel file where I have prepared a simple program for this. So this is my second problem. It is readily available here. So this is our formula. We need to write augment matrix as B1, B2, C1, C2, which is to be converted into I, P, B from C. So I have taken the second column, minus 1, 8 are posted here, and 1 minus 7, B2, and C1 is 1, 2, and C2 is 1, 1. So now this matrix is converted into all these four are written here as an augment matrix. Now elementary operations are being converted here, and finally it is in the form of I, P, B from C. So this is P, B from C. The values are carried to here, 9, 8, 10, 9. This is the required P, B from C. Similarly, if we need to find P, C from B, here I have taken the values of C first, 1, 2, 1, 1. These 1, 2 and 1, 1 is taken first, and B1, B2, minus 1, 8 and 1 minus 7 is taken. So another augment matrix is formed with the C1, C2 first and B1, B2 in the later part. So this is also converted into I into some matrix, and this one will be P, C from B. So 9 minus 8 minus 10, 9. This is our change of coordinate matrix from B to C. So these two are our required change of coordinate matrices for the second problem. So here you can observe that if I want to represent a vector, for example, 2, 4. For example, 2, 4 is my vector in vector space V. So what are the coordinates of C coordinates of 2, 4? 2 and 0. Since to form 2, 4 using C1 and C2, you need two C1s. That is, if you multiply this one with 2, you will get 2, 4. And you don't need this C2. So 0 C2s. 2 C1 plus 0 C2 will give you 2, 4. So the C coordinates of the text 2, 4 is 2, 0. So I will write here 2, 0. Now if I multiply this C coordinates with B, P, B from C, I will get B coordinates. Now 18 and 20 are the B coordinates. B coordinates of that 2, 4. So you want to represent 2, 4, the vector 2, 4 in the language of B. That is as B coordinate vector. You have to write it as 18 and 20. That is the XB, where X is equal to 2, 4. So to get it 2, 4, you have to multiply it with PB. PB is nothing but the vectors in the basis B are to be taken as columns of the matrix. This is PB. So minus 1 and 8, 1 and minus 7. This is our PB. Now PB is being multiplied with the XB. This is XB. PB into XB will give you the vector. So if you multiply these two, you will get 2, 4. Similarly, and this is our PB from C. If you this is change of coordinate matrix, and this is xb. If you multiply pc from b with xb, you will get xc. So if I'm multiplying with these two, I'm getting 2 0. This is nothing but this xc. So all these properties can be taken, can be seen here directly. So this is the problem, second problem. You can also find any problem. Let us check whether it will find the solution for the first problem also. So B1 is 7, 5 and B2 is -3, -1 and C1 is 1, -5 and C2 is -2 and 2. So augment matrix is formed here, and now that is reduced into I into some matrix, and this is PB from C, so that is carried here. So -2, 1, -5, 3. This is the PB from C. Similarly, the same values 1, -5, -2, 2 are to be taken first. So C1 is written here. Those values are carried here. And if these be 7, 5, -3, -1. 7, 5, -3, -1 is here. So this is the augment matrix. And this is the converted I into some matrix. This is nothing but P C from. So this is the required change of coordinate matrix from B to C. So these two are our required answers. This is P, B from C, and this is B, C. So let us test this again. So I want to find a vector which is an addition of these two. So I'm using C1 one time and C2 one time. So then my XC is 1, 1. So if your XC is 1, 1, that means I'm taking and I'm adding these two. So my vector is 1 minus 2, that is -1, and -5 plus 2, -3. So my vector is -1, -3. So the C coordinates of that vector -1, -3 are 1, 1. Now after multiplying this with the PC from B, these will be the B coordinates of the same vector. So the same vector -1, -3 can be represented with B vectors -1, -2. So this is the B coordinate vector of that vector X. That is X is equal to -1, 7, 5 and -2 times -3, -1. And this is the matrix form, of course. This is PB. These columns are taken in this one, in this matrix. And I am multiplying with this XB. After multiplying with XB, I will get the vector X. 1, -1, -3. You can see here. This is nothing but C1 plus C2. Since I have taken 1, 1. Similarly, and this is our PC from B, and this is our XB. 1 minus 2, -1, -2 is our XB. So if I multiply PC from B with XB, I will get XC 1, 1. This is nothing but this. So 1, 1. That means X is equal to 1C1 plus 1C2. That is C1 plus C2. That is C1 plus C2 is -1, -3. So similarly, you can check any problem using this simple software. You can also construct such simple Excel programs with which you can easily and directly find the solutions. Let us find the last one also once. 6 and -12. 4, 2, 4 and 2. This is my B2. And C1 is again 4 and 2. And C2 is 3 and 9. So this is my PB from C. 0 minus 1 by 2 or minus 0.5, 1, 3 by 2 or 1.5. Similarly, this was also constructed directly. So those values are carried here, 4, 2, 3, 3, 9 automatically, and B1, B2 are carried here, and this is our PB files. So we can check for any vector, of course. If I am taking 4, 2, for example, 4, 2 means only 1, 0. I am taking C1 one time and C2 0 times, so 1, 0. That is 4, 2. What will be our XB? 0, 1. So we need to use B1 0 times and B2 1 time. So that is 0. So if you use this 0, 1, here you will get this 1, 0. This 1. So similarly, we can construct programming for higher order matrices also. Just we need to extend the program. That's it. This is what being happened in the real world. So the solutions will come instantaneously by using a proper program. Of course, they use MATLAB or any higher programming, but we can also construct the similar programming by using simple Excel, any spreadsheet program. So let us go back to our PPT again. So similarly, we can solve any problem. So all the 1, 2, 4 problems are solved. We can also find the solutions for the third one also in a similar manner. So this is one more thing, one more problem. Here 3 vectors are given to us in each basis. That A is equal to A1, A2, A3 and B is equal to B1, B2, B3 be basis for a vector space V. And suppose A1 is equal to 4B1 minus B2 and A2 is minus B1 plus B2 plus B3 and A3 is B2 minus 2B3. Find the change of coordinate matrix from A to B. Find XB for X is equal to 3A1 plus 4A2 plus A3. So here we need to find the B coordinate vectors of A1, A2 and A3. So given that A1 is 4B1 minus B2, so A1B, that is B coordinate vector of A1 is 4 minus 1, 0. 0 is since B3 is absent here. And A2 is equal to minus B1 plus B2 plus B3 implies minus 1, 1 and 1 are the respective coefficients of B1, B2, B3. So these will be the entries of our B coordinate vector of A2. Minus 1, 1, 1. Similarly, A3 is B2 minus 2B3. That implies B coordinates of A3 is 0, 1, minus 2. So these 3 column vectors will form our change of coordinate matrix. So here we need to find the change of coordinate matrix from A to B, that is being denoted by P, B from A, is equal to matrix of A1, B coordinates of A1, B coordinates of A2 and B coordinates of A3. That is 4 minus 1 0 minus 1 1 1 0 1. And x is equal to, x is given as 3a1 plus 4a2 plus a3. So xa, that is a coordinate vector of x, is 3 4 1. So since these are the unique scalars, so to find xb we need to multiply pb from a to xa. So we find all these two already. This is pb from a and this is xa. So after multiplying these two, we can get 4 into 3 12 minus 4 plus 0 minus 1 into 3 minus 3 plus 4 plus 1 and 0 plus 4 minus 2, that is 8 minus 3 plus 5 is 2, 4 minus 2 is 2. So these are the b coordinate. These b coordinates, 8 2 2 are the b coordinates, and this matrix, column matrix, is the b coordinate vector of x. Similarly, this is another problem. In P2, find the change of coordinate matrix from the basis B, 1 minus 2t plus t square, 3 minus 5t plus 4t square, 2t plus 3t square, to the standard basis C, 1t square. Find the B coordinate vector of minus 1 plus 2. So let us name the vectors. That this first vector is B1, then this is B2, and this is B3. That is what I can here. So then B is equal to B1, B2, B3. And B1C, we need to find the C coordinates of these three vectors. So B1C is 1 minus 2, 1. Since C is the standard basis, here 1 is the constant and minus 2 is the coefficient of T, the second vector here. And 1 is the coefficient of this T square. So here it is 1 minus 2, 1. And B2C is 3 minus 5 and 4. And B3 is, here the constant is absent, so 0 2 3. B3 is 0 to 3. So these three are the C coordinates of B1, B2, B3 respectively. So the change of coordinate matrix from B to C is P, B from C. So P, C from B, or B1C, B2C and B3C. So those three vectors are written here to form this matrix. So if we need to find B from C, in the problem it was asked to find change of coordinate matrix from C to B. So to find B coordinate vector, we need this one, C to B. So P from P, B from C is nothing but P, C from B inverse. So this is the inverse of this matrix. We are familiar with the matrix inversion, so we can easily find this one. So let x is equal to, it is given that we need to find the B coordinate vector of this one, minus 1 plus 2t. So in standard basis, using the standard basis C, we can easily find the C coordinates of x, which are nothing but minus 1, 2, and t square is option, so it is 0. So C coordinates, we can directly find the C coordinates from the given vector. We need to find xb. So for xb is equal to p b from c xc. So for that we have find this p b from c. So xb is equal to p b from c xc. Here you can observe that this c is adjacent to this xc and this b is adjacent to this xb. So p b from c is this one, which we have found using the inverse of p c from b, and we are now multiplying this with this xc. So after multiplying this, you will get 23 minus 18 plus 0, that is 5, minus 8 plus 6 and 0 is minus 2, and minus 3 into minus 1, 3, minus 2 plus 0, 1. So this is our xb. That is, these are the b coordinates of the given vector. That is, our vector minus 1 plus 2t. Minus 1 plus 2t can be written as a linear combination of the vectors given in B, and these will be the scalars or weights, which will be used in that linear combination. So minus 1 plus 2t is equal to 5 times the given vector, 1 minus 2t plus t square, and 2 times, I think here it is 2, 5, and minus 2 times that second vector plus 1 time the third vector given the problem. So using this, we can find the linear combinations, that is, in which portion, which proportion we need to add them to get the result. That is the interpretation in the real world. So these are the problems related to change of basis. And with this, I am concluding today's session.